Okay, we're going to talk about how indicators work. Now, indicators themselves are weak acids, and normally we write down our weak acid as HA, yeah, and we know that it dissociates A minus, that's its conjugate base, so the ethanoate time, for example, if it's ethanoic acid, and H plus. Well, indicators are also weak acids, so I'm going to call them H in. That's not I for iodine or anything, just an indicator, right, to the weak acid, and it will dissociate into in minus and H plus. And with an indicator, it so happens that this is one color, this is color A, and when it loses its proton, it becomes a different color, so you get a color change. Okay, so let's think what happens. So if we've got an acidic solution, so we've got high concentration of H plus. Well, Le Chatelier tells us that is going to push the equilibrium in that direction. So that means you're going to have color A is going to be that's the color you're going to see. If you've got low hydrogen ion concentration, then Le Chatelier tells us that the low high H plus concentration, so that's high OH minus concentration alkaline, the equilibrium is going to go that way. It will try and make more H plus, so that means you're going to get the in minus predominating, so you're going to see color B. So that's how indicators work. So let's think specific indicators then. So let's do, so if you've got phenolphthalein, okay, phenolphthalein, well, H in there is colorless, whereas the I minus in phenolphthalein, that is purple. So in alkaline solutions, phenolphthalein looks purple. In acid or neutral solutions, it looks colorless, doesn't have a color. And the other one, the other good example, let's have methyl orange. That is in acidic solution, it's red. So, sorry, I'll put down H in is red. And the in minus is yellow. So, right, let's think about how indicators work then. Okay, so what I've got up here is I've got 3 titration curves. I'm going to do something with each one, but let's just look at one of them here. So this is where the end point of your titration is, just there. And number one, this first one is we've got a strong acid. So let's say we've got HCl and NaOH reacting together. And we've got this portion here where it's very steep, right? So you add one drop, and your pH shoots up, as we've seen before, from about you'll shoot up from about 2.5 or something. Go right through 11 with one drop, and it will go all the way to being quite alkaline. That's when you see the sudden color change occurring. So if we look at phenolphthalein, phenolphthalein actually changes around this around high up here. So right, when you're in this part of the spectrum, when you're this part of the thing, phenolphthalein, I'll just call it PP, that's pink, pinky purple. Okay, here in this region it's a mixture, it's pink, and here it's colorless. And the reason for that is, right, phenolphthalein here is it's going to be the I minus is going to predominate, the in minus, sorry, you're going to mostly in minus, so the conjugate base. When it's colorless, it's going to be nearly all the H in the protonated form, and in this pink region it's going to be a mixture of H in and in minus. And you can see when you only add one drop and it shoots right through the colorless all the way to being pink. So you get a very sudden color change. And phenolphthalein is quite easy indicator to use there. Right, let's see what happens with methyl orange. Now methyl orange is the same, it's a weak acid, but it changes. It's actually a slightly stronger weak acid. Phenolphthalein is a very weak acid. Methyl orange itself is a bit stronger, and it changes down here. So methyl orange, below that line there, it's going to be red. And why is it red? Is because the predominant thing you've got is H in, and that's red. Above that red line, it's going to be yellow. And the reason why it's that is because you've got in minus, which is predominant form, which is that color. And in the middle there, you're going to have a mixture of in minus and H in. So it's going to look sort of an orangey color. It's going to look that color, orange. So that's how our indicators work. So with a hydrochloric acid or and sodium hydroxide, you can use either methyl orange, MO methyl orange, or you can use phenolphthalein. Either one will work. You'll get a very rapid color change. You add one drop and the color will shoot from being the acidic color right through to being the alkaline color. And it's very easy, very distinct endpoint. And the endpoint is there. Right, now let's see what happens with a weak acid. Now I'm going to just modify that curve for a weak acid. So a weak acid is, the curve looks something like that. Okay, so just going to rub out that. So now I've got a titration curve for, let's say this is ethanoic acid, so a weak acid plus a strong base, sodium hydroxide. Now you can see there that you can't actually use methyl orange, because if you look, you can't use methyl orange there, because methyl orange, well, at the start of the titration it would be red, and then way before the end point it would go to being orange, not at the end point there, and then you then during the end point, well, before the end point it would be yellow, and after the end point it would be yellow. So you can't use methyl orange, is no good, doesn't work. Can you use phenolphthalein for that? Well, you can see that you can, because the color change occurs in that bit there for phenolphthalein. So it's okay to use that because it's on the steep part of this curve. This curve is like vertical where the phenolphthalein, so you will add one drop and you'll get a color change. Right, now you can probably guess what we're going to do with this one. Is this is going to be a strong acid and a weak base. Now a weak base are things like ammonia, hydrogen carbonate ions. Okay, they're weak bases. Carbonate ions as well. Well, what this curve looks like, I'm going to just modify it a little bit. It's going to be something like that. So I need to rub out the top bit. Now you can see which indicator could we use for this. Well, hopefully you can see now that, well, here's the end point. You can use methyl orange because that's changing down here, but you could not use phenolphthalein because it would be colorless, and then it would start going a little pink towards here, but that's way past the end point. You know, you want it to change color at the end point, and that's not going to happen with phenolphthalein. So just to summarize, a strong acid and a strong acid and strong base, you can use either you can use almost any indicator. And 2 examples I've used phenolphthalein and methyl orange. Because you've got a very steep curve. The curve is steep over a very large pH range, and so most indicators will work. When you've got a weak acid and a strong base, so basically we're talking sodium hydroxide, then you can only use phenolphthalein. Methyl orange is no good at not changing. And then strong acid and weak base, you can use methyl orange, but not phenolphthalein. If you use a strong, what would happen if you had a weak base and a weak acid? Then you just get a sort of wobbly line like that, and you couldn't, so that would be weak acid and a weak base, and you couldn't really use any indicator at all for titration there. So you wouldn't do a titration of a weak, a weak acid and a weak base together. Okay.